All right, in counting courses before, you've probably had the addition, subtraction, multiplication principles, and maybe the division principle. I'm going to assume that you remember addition, subtraction, and multiplication, and let's start by reviewing the division principle of counting. The division principle says if it's convenient to overcount something by a factor of d, go ahead and overcount by a factor of d, and then divide by d at the end. All right, as an example of this principle, let me first define and choose k to be the number of k element subsets of the set 1 through n, or any element set, really. I claim that n choose k is equal to n factorial over k factorial times n minus k factorial. So one way to get a k element set is to permute n, 1 through n, in n factorial ways. And then we're going to keep the first k numbers and get rid of everything else. So that'll certainly be k numbers. We'll use that as our k element set. So here we have the k numbers that we're going to keep and the n minus k numbers that we're going to throw out. Now, if these k numbers had appeared in a different order, we would get the same k element subset. So we are overcounting by k factorial orderings of the first k numbers, which give the same final set. And actually, when we throw away these n minus k numbers, they could have appeared in any one of n minus k factorial ways. And so we're overcounting by n minus k factorial also. So if we correct for the overcounting by k factorial times n minus k factorial, we'll divide by those and we'll get precisely this formula here. So we divide n factorial by k factorial n minus k factorial to get our answer. Now this is a special case of a more general problem. let's define an ordered set partition of n of type A1 through AK, where the sum of these numbers AI is equal to n. To be an arrangement of the numbers 1 through n into subsets called block 1, block 2, etc., with AI elements in block I. And let's define something that looks like n choose k, except it's n choose a1, comma, a2, etc. up to ak. Nobody ever says this out loud, so I'm not sure how to pronounce it. We can say n choose a1, comma, a2, comma, dot, 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 comma, ak. So let's define this to be the number of ordered set partitions of n of type A1 through AK. Now I claim that the number of these is n factorial over a1 factorial dot 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 up to ak factorial. And the proof is nearly the same as what we just did. To create an ordered set partition, we can permute the n numbers 1 through n in n factorial ways, and then we'll cut them into blocks. So we'll permute the set 1 through n in n factorial ways. And we'll break it into blocks. And the blocks will have A1 elements, A2 elements, A3 elements, etc. up to AK elements. And once we've done that, we've got our ordered set partition. Except we have to realize that we're overcounting. There aren't n factorial ways to do this because the A1 factorial ways in which we could have permuted these elements don't make a difference. The A2 factorial ways that we permuted these elements don't make a difference, etc. So we have to divide by the factorials of all the block sizes. And if we do that, so this overcounts by the number of permutations of the blocks. So we have to divide by a1 factorial, a2 factorial, etc., up to ak factorial. All right, now let's look at a similar problem where we're not going to name the blocks block 1, block 2, block 3, block 4, but we're just going to remember the sizes. So let's define an unordered set partition of 1 through n of type A1 through AK. Again, we're assuming that these numbers sum to n. I'm actually assuming that these are non-zero also. So this is an arrangement of 1 through n into unnamed blocks of sizes a1 through an. So for example, 1, 5, 6, 8, 2, 4, 3, 7 counts the same as 1, 5, 6, 8, 3, 7, 2, 4. So we just want to remember which numbers are with which other numbers. It doesn't matter that 2, 4 comes before 3, 7. We're going to count it the same as 3, 7 coming before 2, 4. Now to count these, we need to know how many different blocks have the same sizes as each other. We would never confuse the 2, 4 with 1, 5, 6, 8 because they're different. They're blocks that have different sizes. But if we permute all the n numbers, break them into blocks, and then divide by the factorials of the sizes, that doesn't account for the fact that we're considering these two arrangements to be the same. So if we're given A1 through AK summing to n, all of them positive, and we define mi to be the number of components equal to I, then the number of unordered set partitions of 1 through n of type A1 through AK is n factorial over A1 factorial through AK factorial, m1 factorial, m2 factorial up to mn factorial. Now some of these are possibly 0, so their factorials are 1. And the biggest component we could possibly have here is n, since these numbers are positive and add up to n. So we need to include up to n factorial. So n factorial over a1 factorial through ak factorial, we already understand. That's from the previous problem. So starting with the previous problem, now we have to divide by the overcounting factor corresponding to blocks of equal size. So if there are any blocks of size 2, let's let M2 be the number of them. If there are any blocks of size 3, M3 is the number of them. Maybe there's only one block of size 5. We have to account for permuting these blocks amongst each other in the m2 factorial ways times m3 factorial ways, etc. So that is, we're dividing by m1 factorial, m2 factorial, etc. up to mn factorial. And again, if there are no blocks of a certain size like mn, then mn is 0 and mn factorial is 1, so we're dividing by 1. The end.